A grand welcome to Outens Edu Online. In the previous lectures, we discussed about Laplace Transform, its properties, and did so many problems based on the properties of Laplace Transform. In this lecture, we are going to discuss about the analysis of continuous time, linear time invariant system using Laplace Transform. And we will also discuss about the characteristics of linear time invariant system. The characteristics such as causality, invertibility, and stability by making use of Laplace transform. A continuous time, linear time invariant system means any system which can be represented by linear differential equation with constant coefficient. And a linear system is said to be stable if we are giving an input, we will get an output. Suppose I am removing the input, then the output should tends to 0. Then a linear system is said to be stable. That means without an input, we should not get any output. That's the property of a linear time invariant system. Okay, now let this block diagram represent a continuous time linear time invariant system. So that system can be represented by a linear differential equation with constant coefficient. Now, I am giving an input x of t. Then I will get an output y of t. Suppose I am removing this input x of t, then the output will tends to 0 within a finite duration of time. Then the system is said to be stable. Even though removing x of t, if the output not tends towards 0 or not going to 0, then the system is said to be an unstable system. For example, suppose I am giving an input in this form. Now, after this time t is equal to tau, I remove the input. So what happens? The output should also tends to 0. So let this figure will represent the output. So I am applying the input at t equal to 0 and the input is available up to the time t is equal to tau. Let this figure is I drawn arbitrarily. Let this is the nature of the output. Let this be the point tau. After time t is equal to tau, we have no input. That input is 0. So the output should comes to 0 within a specific duration of time. Either it will come fastly to 0 or it will come slowly to 0 or this will come to 0 in this manner. Anyway, during this duration of time, the output is coming to 0 or tending towards 0. Then only the linear system is stable. If even though after removing this input, if the output is going like this or this going so on for t tends to infinity, then the system become unstable. Okay, so the system is stable means at this point I remove the input, so the output should comes to 0 and finally this will reach 0 within a specific or finite duration of time. Then we say the system is said to be stable. Otherwise the system is unstable. Okay, suppose I am giving an impulse input to the system. An impulse input is represented by x of t is equal to del of t. Then the corresponding output is called impulse response. So the impulse response is usually denoted by the letter h of t. Okay, now we know that the Laplace transform of h of t is denoted by h of s and the Laplace transform of del of t, that is equal to 1. Okay, that means impulse response means when we are giving an input, an impulse input to the system, we will get an output. That output is called impulse response of the system. Now let us discuss the properties of an impulse input. And we know that we can represent an impulse input by this manner. This is 1. This is denoted by del of t, a function of time. This is 0. Okay. So the impulse input is existing only at t is equal to 0. For all other values, t greater than 0 and t less than 0, the value of the signal is 0. That means the signal is not a persisting signal. The signal is equal to 0 after t greater than 0 or t less than 0. So if we are applying this kind of an input, then the output should tends to 0. Since after t is equal to t greater than 0, there is no input. So output should tends to 0. Then only the system is said to be stable. After t greater than 0, there is no input. But if output is going on increasing, then the system becomes unstable. We can define impulse del of t is equal to 0 for t not equal to 0. Okay, then at t is equal to 0, what is the value of the signal? The strength of the signal is 1. That is the area of this line. That is 1. Right. That means integral minus infinity to plus infinity del of t dt, that is equal to 1. This is the definition of an impulse signal. We can write this integral as, I am going to split this integral, that is from minus infinity to 0 minus del of t dt plus integral 0 minus to 0 plus del of t dt plus integral 0 plus 2 plus infinity del of t dt. Since from minus infinity to 0 minus, the value of the signal is 0. So the value of this integral becomes 0. Then again 0 plus 2 infinity, the value of the signal is equal to 0. So this integral is also 0. So 0 minus to 0 plus del of t dt is equal to 1. So we can write this is equal to, that is integral minus infinity to infinity plus infinity del of t dt is equal to 1. That is equal to integral 0 minus to 0 plus del of t dt. This is the correct definition of an impulse signal or a unit impulse signal. If the strength of the signal is A, then we say the impulse of strength A. Okay, this is 1 means the unit impulse input. So we are giving an input like this. So I am going to draw the output arbitrarily. Let this is the output, that is denoted by h of t. So after t greater than 0, there is no input. So the output should comes to 0. Then only the linear system become stable. Suppose like this. Okay, so within this duration of time, the response comes to 0. So the system is stable. Or this may like this is coming to 0. Then also the system is stable. Or this is coming to it and coming to 0. The system is stable. In this all these cases, the value of h of t becoming to 0 within a specific time duration. That again depending the nature of the graph, depending on the system function or transfer function. Or this may be in this manner, this coming into 0. Okay, that depending on the things that inside the box. That is the characteristics of the system. Whether the system is first order, second order, third order, etc. etc. That will determine the shape of the graph. Anyway, since there is no input after t greater than 0, the output should comes to 0 within a specific duration of time. Suppose the output is going on like this. Then what happens? The output is increasing as t tends to infinity. So the system becomes unstable. Okay. That again depending on the location of poles in S-plane. That we will discuss in detail. Impulse response is also called as transfer function. That we will discuss. Suppose I have a system whose impulse response is h of t, and for any input x of t, that is any input x of t, then the corresponding output can be obtained by the convolution of x of t with h of t. That means output y of t is equal to x of t, the input convolute with h of t. Okay, so if we have an impulse response of system, then we can find the response of the system for any other input by making use of convolution. Now I am going to represent this in using block diagram. That is, this is our system. Okay, so this represents the system. Then my input is x of t and y of t is my output. Then the system is represented by the impulse response, that is h of t. So I am representing h of t as system, that is impulse response. Let the Laplace transform of x of t is x of x. Then the Laplace transform of h of t is h of s. And Laplace transform of y of t is y of s. Okay, that means y of t is equal to x of t convolution h of t. And convolution in time domain is same as that of the multiplication in Laplace domain. From this equation, we can write, I am taking the Laplace transform on both sides of this equation. That is y of t become y of s. And the Laplace transform of x of t convolution h of t, that is equal to x of x into h of s, or h of s is equal to y of s divided by x of x. Okay, this h of x is called system function or transfer function of the system. That is system function or transfer function of the system. Okay, so from this equation we can write y of s is equal to x of x into h of s, x of x into h of s, or h of s is equal to y of s divided by x of x. Okay, now we can represent transfer function in pole zero form. That is, h of s can be represented as a gain k into s plus z1 into s plus z2 up to s plus zm divided by s plus p1 into s plus p2 up to s plus pn, where s is equal to minus z1 minus z2 up to minus zm are the zeros of the transfer function, and s is equal to minus p1 minus p2 up to minus pn are the poles of the transfer function. When we are putting those values of s in numerator, that will make the transfer function h of s is equal to 0. That is called zeros of transfer function. When we put those values of s in denominator, which will make the transfer function infinity, is called the poles of the transfer function. That means s is equal to minus z1 minus z2 up to minus zm are the zeros of transfer function. When we put s is equal to minus z1, this entire function h of s become 0. Similarly, s is equal to minus p1 minus p2 up to minus pn are the poles of transfer function. When I am putting s is equal to minus p1 in denominator, that will make h of s is equal to infinity. There are the poles of the transfer function. Physically existing the system or physical realizability of the system, m should be less than n. That is, m should be less than n. M means the number of zeros should be less than number of poles. Then only the system will exist. Exist means system is physically realizable. That means physically realizable. Okay, if m is greater than n, that is number of zeros is greater than number of poles, then the system does not exist. That is not physically realizable. For example, I am writing h of s is equal to some gain, that is, let me the 10 into s plus 1 divided by s plus 2 into s plus 3. Here we have a 0 at s is equal to minus 1, a pole at s is equal to minus 2 and s is equal to minus 3. So m is equal to 1, that is number of 0 is 1 and number of pole is equal to 2. So the system is physically exists. On the other hand, suppose h of s is equal to some gain 5 into s plus 1 into s plus 2 divided by s plus 3. For this transfer function, we have a 0 at s is equal to minus 1 and at s is equal to minus 2 and only one pole at s is equal to minus 3. That means m is equal to 2, number of zeros is equal to 2 and number of poles is equal to 1. This system does not exist or that is not physically realizable. So for a system should be physically exist, number of zeros should be less than number of poles. The reason for this we will discuss in detail in the coming sessions. Okay. Now we are going to discuss about the characteristics of the linear time continuous system. That means the characteristics such as causality, stability and invertibility, and based on that we will do some problems. That is characteristics of continuous time, linear time invariant system. Okay. First characteristic is causality. Okay. Now we are going to discuss what is a causal signal. We know that a signal is said to be causal if the signal existing only for t greater than 0. An anti-causal signal is a signal existing only for t less than 0. If a signal existing for t less than 0 and t greater than 0, that signal is non-causal signal. Now we are going to relate the causality of continuous time system in terms of impulse response. A linear time invariant system is said to be causal. That means if system is causal, then the impulse response h of t is equal to 0 for t less than 0. This is the relation of impulse response and causality of a linear time invariant system. H of t is equal to 0 means for t less than 0. So h of t existing only for t greater than 0. For example, I am drawing like this, let h of t like this. This is the impulse response as a function of time. So the signal is existing only for t greater than 0. Or let the signal be like this. This is our h of t. Then I can draw h of t like this. These all are h of t. That means h of t is available only for t greater than 0. For t less than 0, h of t is equal to 0. That is the property of a, then the system is said to be causal. Okay. Now we know that impulse response should tends to 0 as t tends to infinity. Then only the system becomes stable. Suppose this is going to 0. During this time duration or during a specific time duration, the system is stable. Suppose the impulse response is going on increasing as t tends to infinity, then the system becomes unstable. Suppose, for example, the impulse response is going like this, goes on as t tends to infinity, that is increasingly going. Okay, then the system is unstable. Or this impulse response can increase like this, going to infinity as t tends to infinity, then also the system becomes unstable. For a system is causal means impulse response existing only for t greater than 0. And that impulse response should tends to 0 as t tends to infinity. T tends to infinity means a large t or during a specific time duration tends to 0, then the system is said to be stable. That is the relation between causality and stability. Okay, in short, a system is said to be causal if impulse response existing only for t greater than 0. Then that response tends to 0 as t tends to infinity, then the system is said to be stable. Okay. Now, we know that what is the relation between ROC and causality. For a causal system is said to be stable, then the region of convergence towards the right hand side of the S plane. This is my S plane. I am representing sigma j omega. Let this be some minus 1. This is origin 0. So for a causal system, the region of convergence is towards the right hand side of the S plane. Then in this figure, the ROC consisting of j omega axis or ROC consisting of imaginary axis, then the system is said to be stable. If the ROC does not consisting of imaginary axis, then the system is unstable. For example, I am drawing this figure. Like this is my sigma j omega. Let this is equal to plus 2. Okay. Let this is my ROC, region of convergence in S planes. Since region of convergence is towards the right hand side of the S-plane, so the system is causal. But region of convergence does not involve j omega axis. This is our j omega axis. Okay, so the system is unstable. So this is the relation between the region of convergence and causality and stability. The system is said to be causal, then region of convergence is towards the right hand side of the S-plane. And if the system is stable, then the region of convergence should consisting or should containing the j omega axis. In this figure, this containing j omega axis. In this figure, the ROC is from +2 and towards the RHS. The system is causal, but at the same time, the system is unstable. Since this is not containing the j omega axis. The reason we will discuss. Okay. Suppose I have a transfer function or impulse response h of s is equal to 1 divided by s plus 1. So we have a pole at s is equal to -1. So in S-plane, I am marking the pole at s is equal to -1. This is a pole at s is equal to -1. This is my j omega axis, sigma, and our S-plane. Now what is the region of convergence for this? The ROC for 1 by s plus 1 is real of s, that is sigma greater than -1. So this is -1. So this region is the region of convergence. So the signal is a causal and this consisting of j omega axis. So we said that if region of convergence consisting of j omega axis, then the system is said to be stable. Okay, now let us find h of t, that is a time response of impulse response. Time domain representation of impulse response, h of t, that is the inverse Laplace transform of 1 by s plus 1. That is equal to e raised to minus t. Okay, now I am going to draw h of t, that is impulse response as a function of time. At t equal to 0, the value is equal to 1. This will exponentially decays to 0. So the impulse response decays to 0 within a specific time duration. Then the system is said to be stable. We know that if the system is said to be stable, impulse response should tends to 0 as t tends to infinity. Infinity means a large duration of time or a specific duration of time. Okay, so the system is stable. That means ROC consisting of j omega axis. So the system is a stable system. Now consider my transfer function h of s is equal to 1 divided by s minus 1. So I have a pole at s is equal to 1. So in S-plane, I can draw a pole at s is equal to 1. This is sigma j omega. For this, we know that ROC is equal to real of s, that is sigma greater than 1. So this is the region of convergence. Okay, so this region of convergence does not consisting of j omega axis. The ROC does not consisting of j omega axis, the system become unstable. Now let us find the time domain response of h of s. That is h of t is equal to inverse Laplace transform of 1 by s minus 1. That is equal to e raised to t. We can draw e raised to t. At t equal to 0, the value is equal to 1. As t increases, the impulse response is exponentially increases to infinity. Then the system becomes collapsed. So when t increases, the response increases. In this first case, this decreases to 0. The system is stable. And response is increases exponentially. That means the system is unstable. So for a large duration of time, the magnitude of the impulse response becomes infinity. So the system becomes collapse. So the system is unstable. The reason for that is, here the pole is lying on the LHS of the S-plane. That means for a system to be stable, then the poles of the system should lie on the LHS of the S-plane. Here the pole is lying on at s is equal to 1. This is the RHS of the S-plane. So if any poles lying on the RHS of the S-plane, then the impulse response will grow to infinity, either exponentially or sinusoidally. Anyway, goes to infinity. Suppose for a second order system, this will goes like in this manner towards infinity, and the system become collapse. Okay. So for condition for stability is all the poles of the system should lie on the left hand side of the S-plane, then the system is stable. If any poles lying on the RHS of the S-plane, the system becomes unstable. If zeros have any role in stability? Zeros have no role in stability. But the zero will determine the speed of the response. So response speed can be determined from the zeros of the transfer functions. But stability is determined from the poles of the transfer function. Okay. Now, a system is said to be anti-causal if h of t is equal to 0 for t greater than 0. Linear time invariant system is said to be anti-causal if the impulse response h of t is equal to 0 for t greater than 0. So the impulse response existing only for t less than 0. Or pictorially we can represent this is our h of t. Okay, function of time. Suppose this is in this manner. Okay, or some in this manner or some in this manner. Okay, so h of t is existing only for t less than 0 or towards the LHS of the time axis. Then we said that the system is anti-causal. That means if the h of t tends to 0, that is impulse response is tending towards 0, then the anti-causal system is said to be stable. If this is goes on increasing as t increasing towards minus infinity, that is means t decrease. If this is goes on like this, then system become unstable. Okay, that means for an anti-causal signal, for an anti-causal linear time invariant system, h of t existing only for t less than 0. For t greater than 0, the value of h of t is equal to 0. As this h of t goes to 0, then the system is said to be stable. Then what about the region of convergence of an anti-causal signal? We know that for an anti-causal signal, the region of convergence is towards the left hand side of the S-plane, towards this side of the S-plane. Okay. So suppose we have pole at -1. For an anti-causal signal, this is the nature of ROC. Again, depending on the, if we have pole at S is equal to 1, then this is the region of convergence towards LHS of the S-plane. This is our S-plane, j omega axis, and our sigma. Okay, sigma S-plane. So for a anti-causal signal, the impulse response existing only for t less than 0, and for t greater than 0, impulse response equal to 0. And impulse response tends to 0 as t tends to infinity, then the system is said to be stable. And the region of convergence is towards the LHS of the S-plane. Okay. Next is stability. As we already told that a system is said to be stable if the impulse response tends to 0 as t tends to infinity. Or we can say a linear time invariant system is said to be stable, that is bounded input, bounded output stable, if the impulse response is absolutely sum. If the impulse response is absolutely integrable, that means integral minus infinity to infinity, the magnitude of h of t dt is equal to finite. It should have finite value. Finite value means it is less than infinity. If this condition is satisfied, then the system is said to be stable. The condition for stability is, for a causal linear time invariant system is said to be stable, then the ROC should contain the j omega axis. Otherwise, the system becomes unstable. So this is absolutely integrable. That means this is less than infinity. That means the value of this integration is a finite quantity. Then the system is said to be stable. For example, this is an integration of h of t. So we have integration means area under this curve. So it has a finite value. The system is stable. Suppose this goes on increasing, then the value goes to infinity. So that is not absolutely integrable. That is an unstable system. Next characteristic is invertibility. Okay, suppose I have a system. Let the transfer function is indicated by h1s, and let x of t is the input, and I got an output y of t. Now I am giving this y of t as an input to another system whose transfer function is h2s. That is, y of t is the input to the system, and I got the output as x of t. Then these two systems are said to be invertible. That means like the system is represented by S1 and system is represented by S2. Then we can say S2 is the inverse system of S1, or S1 is the inverse system of S2. That means S1 and S2 are inverse to each other. That means we will get x of t will produce y of t. This y of t is giving an input to another system that will produce x of t. That is the input to the first system. That is a condition for invertibility. That means if system is said to be invertible, if h1 of s into h2 of s, that is equal to 1. That is, the product of these two impulse response or transfer function is equal to 1, then the system is said to be invertible. So we can write from this equation, we can write h2s that is equal to 1 by h1s. This is the condition for invertibility of a system. For example, I have an ideal differentiator. That means a differentiator with zero initial conditions. That can be represented by y of t is equal to dx of t by dt. This is a differentiator. Okay. This operation is a differentiation. So this can be called as a differentiator. Now what is the Laplace transform of this? Y of s is equal to s into x of x. This implies y of x by x of x, that is equal to s. Let that is equal to h1s. That is a transfer function of a differentiator, that is equal to s. Now consider an integrator. Integrator means a device that performs the integration operation. Now we are assuming an ideal integrator having zero initial condition. That can be represented by y of t is equal to integral 0 to t x of tau d tau by assuming zero initial condition. Now taking the Laplace transform, y of s is equal to x of x by s. This implies y of s by x of x, that is equal to 1 by s. This is a transfer function of an integrator. Let this is equal to h2s. Now the product of h1s and h2s, that is h1s into h2s, that is equal to x into 1 by s, that is equal to 1. This implies h2s that is equal to 1 by h1s. That means an integrator is an inverse system of differentiator, or differentiator is an inverse system of integrator, so that both systems are invertible. This is an example of an invertibility of the system, an integrator and a differentiator. Okay, right. Now we have question h of s is equal to e raised to s divided by s plus 1, and we want to check the causality of the system. Check the causality of the system. Okay. Now for this transfer function, that is 1 by s plus 1 is multiplied by a term e raised to s. Now for this 1 by s plus 1, we have a pole at s is equal to minus 1. So in s plane, we can draw this as pole at s is equal to minus 1. This is our sigma axis, j omega axis 0, our s plane. So the region of convergence for this signal is real of s greater than minus 1. That is ROC is equal to real part of s, that is equal to sigma greater than minus 1. This is the region of convergence. This is the region of convergence. But what is the condition for causality? A system is said to be causal if impulse response h of t is equal to 0 for t less than 0. Causal means h of t is equal to 0 for t less than 0. This is the condition for causality. Now our function is e raised to s divided by s plus 1. We have a property. Laplace transform of x of t minus t0, that is equal to e raised to minus st0 into x of x. We can apply this property in this problem. Here the signal is delayed, but here the signal is advanced. Similarly, Laplace transform of x into t plus t naught, that is equal to e raised to s t0 into x of x. This is an advanced signal by t0 unit. Okay, suppose this is our signal x of t. I am simply drawing x of t. Then x of t minus t0 is drawn like this. This is our signal x of t minus t0. That is the delayed by t0 unit. This is our x of t. And this is an advanced signal that can be drawn as this is minus t0. So this is the signal x of t plus t0. This is the advanced signal. H of s, suppose h of s is equal to 1 by s plus 1. The inverse Laplace transform of this is h of t, that is equal to e raised to minus t into u of t. Now our h of s is multiplied by the term e raised to s. That means this is advanced by 1 unit. So this is equal to, the inverse of this function is equal to e raised to minus t plus 1 into u of t plus 1. And again e raised to minus t plus 1 into u of t plus 1. That is, the signal will starting from t is equal to, that means the impulse response is starting from t is equal to minus 1. This is the advance. So in between minus 1 and 0, the impulse response have some value that is not equal to 0. The system is not causal. On the other hand, if this is equal to minus s, then what happens? Then we can draw like this. So the system become a causal system. Causal. This is an advanced system, that is e raised to s. So the value of impulse response in between minus 1 and 0 have some finite value. So the system is non-causal system. This figure I drawn arbitrarily. Okay. So this is a non-causal. Now we have, let this is our some h of s. Then for this I am taking only this term. So the inverse of this is equal to h of t is equal to e raised to minus t u of t. So I can draw this as e raised to minus t is exponentially decaying to 0. This is the function h of t. Okay. So as t increases, this is exponentially going to 0. At t equal to 0, the value is equal to 1. Now, using this property, what happens? This is advanced by a unit 1. So the signal can be drawn as starting from minus 1. This is equal to e raised to minus of t plus 1 into u of t plus 1. So instead of starting from 0, this signal will start from here and goes to 0. So in between minus 1 and 0, the signal have this value that is not equal to 0. So the system is a non-causal system. Okay. So this is the actual figure representing e raised to s divided by s plus 1. On the other hand, this is e raised to minus s. Then what happens? Then we can draw this is equal to 1. Then the impulse response will look like this. That is e raised to minus of t minus 1 into u of t minus 1. This system is a causal system, since impulse response is existing only for t greater than 0. But this for minus 1 less than minus 1 less than t less than 0, the signal have this much value that is not equal to 0. So that is a non-causal system. I think the concept is clear. So our question is h of s is equal to s minus 1 divided by s plus 2 into s minus 3. Check the stability and causality of the system. Okay. Now, we want to check whether system is causal, anti-causal and non-causal. That again depending on the region of convergence. Here the region of convergence is not specified. Consider 3 regions of convergence in this case. One region of convergence is for, one case is for causal and other is for anti-causal and for non-causal case. In S-plane, a 0 at S is equal to 1. 0 have no role in determining the region of convergence. Region of convergence is completely depending on the location of poles. And one pole at S is equal to minus 2 and a pole at S is equal to 3. That is 1, 1, 2, 3. A pole. Okay. So we can consider a region of convergence, a region greater than 3. This is one ROC. Here the region of convergence is real of S that is greater than 3. First ROC. Okay. Then we can consider a region of convergence, the region in between minus 2 and 3. This region. Okay. That is this region. That means ROC as minus 2 less than sigma less than 3. This is a second ROC. This is a ROC 1. Then region of convergence 2. And we can also consider a region of convergence in this region. That is sigma less than minus 2. So this region ROC is sigma less than minus 2. Now we want to check the causality and stability of this transfer function in these 3 regions. First region is in this region, then in this region, and again this region. Okay. Now let us do one by one. Now we can write h of s is equal to, I am going to write h of s by making use of partial fraction so as to find h of t. A divided by s plus 2 plus b divided by s minus 3. Right. Now find the value of a and b. What is a? A is equal to, we have pole at s is equal to minus 2. So I am using the method of residue. That is s plus 2 into this entire function. That is s minus 1 divided by s plus 2 into s minus 3. This is evaluating at s is equal to minus 2. This s plus 2 and s plus 2 gets cancelled and put s is equal to minus 2 in the remaining terms. So minus 2 minus 1 divided by minus 2 minus 3. This is equal to minus 3 by minus 5 or is equal to 3 by 5. So the value of A is 3 by 5. Now value of B, that is equal to s minus 3 into this function, that is s minus 1 divided by s plus 2 into s minus 3 is evaluating at s is equal to 3. Now this s minus 3 and s minus 3 gets cancelled. Then put x is equal to 3 in the remaining terms. That become 3 minus 1 divided by 3 plus 2. That is equal to 2 by 5. So the value of b is equal to 2 by 5. So we can write h of s is equal to a is 3 by 5 into 1 by s plus 2 and b is 2 by 5 divided by 1 by s minus 3. Now take the inverse Laplace transform. Okay. Now our h of s is 3 by 5 into 1 by s plus 2 plus 2 by 5 into 1 by s minus 3. Now first we consider region of convergence ROC, real of s, that is sigma greater than 3. This is a region of convergence, that is I am pictorially drawing. This is our 3. This is the region of convergence. Okay. This is our j omega sigma x6 S plane. So ROC is towards the right hand side of the S plane. So the system is a causal system. Okay. Now taking the inverse Laplace transform of this. This become h of t is equal to 3 by 5 into e raised to minus 2t u of t plus 2 by 5 into e raised to 3t into u of t. Now what about the stability of the system? The system is causal since ROC is towards the right hand side of the S-plane. Now what about the stability? Stability means h of t tends to 0 as t tends to infinity. Then the system is said to be stable. I can draw this term. This term is 3 by 5 and t equal to 0, the value is 0, 3 by 5 and exponentially decays to 0. Then what about this term? This is e raised to 3t. So t equal to 0, the value is 2 by 5 and this is exponentially increases to infinity. So t tends to infinity, this portion of the response goes to infinity. So the system becomes unstable. So the system is causal and unstable if region of convergence is greater than 3. That is the first. Now consider the second case. Now region of convergence, that is real of s, that is minus 2 less than real of s, that is sigma less than 3. Okay, now take the inverse Laplace transform from this. Now our region of convergence is minus 2, 3, this region. This is our region of convergence. Okay, for this portion of the signal, the region of convergence is towards the left hand side. That is, this is an anti-causal signal. So the Laplace inverse of this is equal to 2 by 5 into e raised to 3t into u of minus t. So ROC is towards the LHS of the S-plane for this portion of the signal. Okay, now for this portion of the signal, region of convergence is towards the RHS of the S-plane. So this is a causal, that is ROC is towards this plane, that is minus 2. If ROC is towards this that means anti-causal. So the Laplace inverse of this portion is 3 by 5 into e raised to minus 2t u of t. So this is the h of t. Okay, I think it is clear. So this is a causal signal and this portion is an anti-causal signal. So let us draw the h of t. Now for this portion of the signal, the h of t is at t equal to 0, what happens? The value is 3 by 5. Then exponentially going to 0. Okay, so this is existing for t greater than 0 and this portion is stable and causal. Okay, this is actually minus 2 by 5. So we can draw the signal as 0. I am going to draw this portion of the signal that starts from minus 2 by 5 and this is ROC minus 2. This is goes to here and for this is goes to the look like this. So the response will look 3 by 5 to here and during this portion this is minus 2 by 5 and goes to this. This is value 3 and this value is minus 2. So the impulse response is absolutely summable. The impulse response h of t is absolutely integrable and this is the value area under the curve during this duration and this is the area under the curve during this duration. So that you have a finite value. The system is stable. Impulse response is existing for t greater than 0 and also for t less than 0. That means this portion is causal, this portion is anti-causal. That means the net system is a non-causal system but the system is a stable. So during this ROC, the system become non-causal but a stable system. Okay, now the case is region of convergence ROC, that is real of s less than minus 2. That means this is our S-plane sigma j omega, the pole at minus 2. So This is the portion of ROC. So for this portion of the system, this is anti-causal. For this portion of the system also, this is lying towards the LHS of the S-plane. So ROC is sigma less than minus 2. That means an anti-causal system. Okay, now we want to take the stability of this anti-causal system. Now, the inverse of this portion become minus 3 by 5 into e raised to minus 2t u of minus t. And for this portion, this become minus 2 by 5 into e raised to 3t into u of minus t. This is h of t for the anti-causal system. That means ROC is less than minus 2. Right. Now, what about the stability? We can draw this portion of the response. Starting from minus 3 by 5 and t is less than 0. Okay, this is let h1t. Okay, so as t less than 0, what happens? This figure is exponentially grows to infinity as t is going towards minus infinity. So this portion become unstable. Okay, now what about this portion? This portion, as t tends to portion, start from minus 2 by 5 and goes to 0. So this is a stable portion, but this part is an unstable part. This goes to infinity exponentially. So the system become unstable. That means system is anti-causal and unstable. So the system is stable when ROC is lying between minus 2 and 3. So the system is a non-causal stable system. And a causal, when ROC is sigma greater than 3, the system is causal and unstable. And when ROC is sigma less than minus 2, then system is anti-causal but unstable. In the next session, we will discuss about the linear time invariant system. That is about the differential equation with constant coefficient. And about interconnections of systems. And we will do so many problems related to the entire topics. Okay, thank you.